So I'm making a video about a physics problem I did recently. This physics problem surrounds some kinetic and inelastic collisions, and you have to set up the different situations asked of you in the problem. And setting up those situations, you're able to find the total distance that the system travels before it stops, and you're able to find the total time that the system will take to come to rest. So the system looks something like this. There's an angle theta. If you wish to do this problem yourself, assume theta is 30. These are height r, and the length between these two half-pipe things is 4r. And during this forearm, there is some kinetic friction, which is mu k, equals to 0.05. And this problem surrounds two different blocks that we have. One block is M2, one block is M1. They're assumed to be point masses. M1 weighs 1 kilogram, M2 weighs 2 kilograms. And let's call this point point A. Let's call this point B. And we have a few different situations that we have to consider here. The first situation is when we take this guy, we put him up here, and we drop him, we slide him down the ramp, and he decelerates some amount before colliding with M2. The next one is switched around, where M2 slides down and then collides with M1. And then you have to repeat that process, but instead of the objects sticking to one another, instead of it being an inelastic collision, it ends up being an elastic collision. So you have to calculate the speeds after they collide, and then you have to do some absolute madness with the decelerations and then coming up and back down the ramp and then recolliding with one another. We'll get to that soon. But I'm going to start off with two little cute derivations that you can do to find the total length that these systems cover inelastically before coming to rest. So if we think of M1 right here being dropped on M2, we have some amount of potential energy being up here, and that potential energy is just mgr. And we know that on our way to this point B, we're going to lose 2r times mu k mg, because we have the mass times gravity, we have the weight times mu k over a distance. And you'll notice that this has the unit joules and this has the unit joules, for obvious reasons. And because we've set up this identity, we could take out an mgr and rewrite this as 1 minus 2 mu k. And we know that this is going to be equal to the kinetic energy at collision. And we also know that happens to be equal to 1/2 mv squared. And what you can do is you can solve for v in this situation to find the velocity at collision. And after we find that velocity at collision, we'll multiply it by 1/3, because the mass of the system triples, so the velocity must be thirded. So we know v after is 1/3. Algebra is left as an exercise to you if you really wish to perform it. 2gr, 1 minus 2 mu k. And having this, we can plug this back into the kinetic energy theorem. And plugging this back into the kinetic energy theorem, we will find that Ke after is 1/2 times 3 kilograms times 1/3 2gr 1 minus 2 mu k. That's all squared. And if you solve this out, and if you plug in our values for mu k, which is 0.05, you will find that the kinetic energy remaining after this collision is 3/5 of a joule. And then, knowing that we have 3/5 of a joule after we complete the collision, we want to know how long the system will take to stop. So we're wondering how much of r times r mu k times mg, we could plug in for mg, joules on one side, joules on the other, same as before, and we'll find that r must be equal to 4, or 4r is the answer for how much kinetic energy must be taken out of the system for it to stop. So what does this mean? This means that M1 will start here, slide down, come across, and upon hitting this guy, it will have 4R of remaining kinetic energy. So it will slide across here, which is 2R, and it will lose some amount of this energy. It will slide up the ramp, come back down, because this is considered to be frictionless in the problem. So it will slide back up, slide back down, and then it will cover another 2R before stopping. Cool. You can repeat this exact same process for M2 dropped on M1. But our potential energy this time is going to be 2 mgr, just because it's twice as heavy. And minus, same as earlier, 2 mg mu k 2r. Take out 2 mgr. 1 minus 2 mu k equals ke collision equals 1/2 mv squared. Do the same thing as earlier, solve for velocity and multiply by 2/3 because the system's weight doesn't change as dramatically, it just goes from 2 to 3. So here we have 2/3 root 4gr, 1 minus 2 mu k equals 1/2 mv squared. And plugging this back in, and then plugging it back into the kinetic energy theorem, solving this out, we'll find that we get 6/5 of a joule. And conveniently, 6/5 of a joule happens to be twice as much as this, so we know the answer here is 8R. So 8R of energy, I guess you could say, will be remaining in the system after 2 comes down here and hits M1, which means we'll go 1, 2, slide up, down, 3, 4, 5, 6, slide up and down, 7, 8. Cool. Now, the part of this problem that's a lot less fun is when you have to deal with the kinetic kind of stuff. Because when you deal with the kinetic kind of stuff, you need to deal with stuff like, okay, you have M2 coming down in M1. What speed does M1 come off at? What speed does M2 continue at? And what is the behavior after it comes back up, comes back down? Where is M2 at when it comes back down and when they collide again? What are the speeds after that? You know, if they come back here and then come back up and then come back down, and then you have all these differently behaving blocks. It's a lot to keep track of. It really is a lot to keep track of. It took me a few hours of algebraic computation. A few of those hours, it was more than a few hours. I wasted a couple hours because I just got the complete wrong answer. And then eventually I kept at it and I got something a little bit more reasonable. At least reasonable according to my physics professor. So I will not bore you with d equals VIT plus 1/2 AT squared. To solve for time for probably 3 more hours if I'm here to do every single calculation by hand, but I'll tell you that this is how you do it, mixed with a little bit of t equals root 2d over a. Perfect. So now I'm going to tell you the answers that I got for the inelastic situations. I got 4.226 seconds for M1 dropped on M2. For M2 dropped on M1, I got 6.85 seconds. And then for the elastic, I got 8.64 seconds for M1 on M2. And then I got 16.30 seconds for M2 on M1. And then the total distances that these guys travel. For M2 dropped on M1, I have 2.492 R is when M2 stops. And then 3.078 R is when M1 stops. And then for M1 dropped on M2, I have 0.068 M1 stops and 2.03 M2 stops. And these are all the final answers. There are a lot of answers in this problem, and that's what makes it partially so difficult. We have distances here, distances here, distances here, times here, and times here. So there's a lot that goes into solving this problem. But in all, it's a battle of attrition. You just have to be really rigorous with your algebra and keep all your ducks in a row. And if you have the knowledge to code this. And you'll probably get a more accurate answer than I did, because if you crack 1,000 eggs, you're gonna get a double yolk. So that's my video. I hope you enjoyed watching it, and have a good one.